Everyone, my name is Xin Li. My presentation is about the Multi-GNSS real-time precise position service and the initial assessment of BDS3. The presentation mainly includes the Multi-GNSS hourly orbit determination, clock estimation, and the Multi-GNSS PPP ambiguity resolution. And I also present some initial results of BDS3 and finally some discussions. This is the tracking stations selected from the hourly for the hourly multi-GNSS orbit determination. These hourly observation files are from the CDDS, IGN, and the BKG archives. Totally more than 150 hourly stations, but we select 100 globally distributed stations, as shown in this figure. And this is the multi-GNSS real-time stretch hosted by the Germany BKG cluster. We selected about 70 real-time stations. All of these stations support multi-GNSS. And this is the current our multi-GNSS hourly orbit determination strategy. Before we provided we generated the orbit every 3 hours and with the daily solution. Recently we try to reduce the prediction length and enhance the solution. So we use 48 hour solutions and hourly update. For this hourly orbit determination, we download the hourly files from the CDDS, IGN, and the BKG FTP, and merge them with the two GFG relics, and also download the broadcast and do some quality check, and then generate the 40 hours initial orbit, and then do the pre-processing and least square estimation and generate hourly SP3 files. This is the summary of the comparison of the old and new strategies. The main difference is that we changed the update interval from 3 hours to 1 hour, from 1 day solution to 2 day solution. And we also reduced in order to process faster, we reduced the processing interval from 5 minutes to 10 minutes, and also reduced the ISB and the IFB parameters, and used some technical tweak for fast processing. And this is the comparison of the computation of older and new processing strategies. For the older strategy, we can say that it takes about more than 2 hours. That's why before we use 3 hours update interval. Currently, the processing time is reduced to about 50 minutes, and then we can implement the hourly update. And this is the comparison of orbit accuracy with the precise final orbit product from Wuhan University. We can see that forward directions, for Beidou forward directions, the accuracy are improved significantly. As we know, the radial direction is most important for position. We can see that for GEO, for IGSO, the accuracy can be improved very significantly. For MU also there are some improvement. For the GPS, GLONASS, and the Galileo with the new strategy, the accuracy can also be improved. With the hourly orbit and the real-time clock, then we can do the PPP ambiguity resolution. Here, the blue denotes the float solution, and the right line is the fixed solution. The left column is GPS, the comparison of GPS float solution and the GPS fixed solution. This one is GPS and the GLONASS float solution and the fixed solution. This is GPS Beidou, GPS Galileo, and the last clone is the comparison of float solution and fixed solution of the GPS, GLONASS, Galileo, and Beidou. We can see that for GPS or dual system compilation or full system compilation, we can find that the fixed solution can always improve the position accuracy. In fact, in our new product, we include the GPS, GLONASS, Galileo, Beidou, and QGISS, because QGISS now only have one satellite, so in the PPP ambiguity resolution, we only use 4 systems. And this figure is a natural figure for to comparison the float solution compare with comparison of float solution, float PPP and fixed PPP for the GREC 4 system solution. We can see that even for 4 system multi-GS solution, the fixed solution can also always improve the position, especially the convergence. In this solution, it's also well to notice that in the multi-GS we fix GPS and ambiguities, GLONASS ambiguities, and Galileo ambiguities, and Beidou ambiguities. But we don't fix the ambiguities between GPS and GLONASS because of the difference frequency. This is the GPS fixed solution compared with the GREC 4 system fixed solution. The blue line is the GPS fixed solution. The red line is the 4 system fixed solution. And this is the east, north, and up. We can see that the multi-GNSS combination can also significantly improve the fixed solution. And this is to demonstrate the benefit in some constrained environment. Here we choose different, here is the fixed solution and the different cutoff elevation, 7 degree, 10 degree, 15 degree, and 20 degree, and 30 degree. We can find that even usually at 7 degree, the multi-GNSS combination, the blue line and the red green line can always improve the accuracy and especially the convergence. Along with the increasing at cutoff, the GPS only solution can be not stable, but the multi-GNSS solution is still very reliable. This is we think that this would be the biggest benefit of multi-GNSS for precise position. And then I give some short initial assessment for the Beidou 3 new satellites. Now we have 5 experimental new satellites. This is the ground tricks of the new generation Beidou satellites. And here is the signal for this experiment satellites. They have B1I, B3I, B1C, B2A, B2B signals, 5 frequencies. We use a private receiver from the University of National Defense Technique. The antenna type is a tremble antenna, and the location is in the Wuhan University. And it can track GPS I1, I2, I5, Galileo E1, E5A, E5B, and the Beidou E1, B1, B2, B3 for the old satellites, and B1I, B3I, B1C, B2A, B2B for the new generation satellites. With the data set, we do some analysis. We can say that this is the multipath comparison against the elevation. This figure is for GPS satellites. We can say that the noise is larger when the elevation is lower and no systemic error. This is the Galileo. There is a similar performance, but we can see that for the Beidou 2 satellites, for example, C14, there is very strong systematic error. This is called this is a very famous Beidou code base. This result is the C32 for C32, 33, and 34 is a new generation Beidou 3 satellites. We can see that this problem is already solved in the Beidou new signals. Here shows 3 new sets with 5 signals. We can see that no seismic errors. And here we also show the another very famous pairs is the triple frequency K-phase multipass and Lloyd. Is calculated by we can form 2 atmosphere free combination between the first and the second frequency, and the atmosphere free combination between the second and the third, the first and the third frequency. Then we can get a geometry free and atmosphere free combination. It mainly includes ambiguity, carrier phase multipass, and noise. We can say that this is GPS. This is a very famous carrier phase pairs. We can say that in GPS, there is a very strong seismic error. And for the Beidou 2 satellites, we can, for example, C1 also there are seismic errors. It's smaller. It's about 2 centimeters. This figure shows the Galileo result. We can see that for the Galileo triple frequency, there is no such seismic error. Unfortunately, for the new generation Beidou 3 satellites, we can also see that C32, C33 also no such seismic error. It means that this problem is also resolved for the new signal. Finally, some discussions. Now we have more and more new satellites, new signals, and more new frequencies. We will try to handle various pairs and to achieve best accuracy and the best performance of ambiguity fixing, and also the efficiency, especially for real-time file system processing, is also very important. And finally, the stability is also very important, especially for the new Beidou satellites.